In recent years, the integration of electronic circuits into textiles, including wearable antenna, is the new evolution for the Internet of Things. These are the existing textile antennas. The existing design doesn't always provide a reliable link between a receiver and the transmitter. Plus, these antennas are rigid and not flexible. The performance deteriorates once it is being washed or crumpled. Moreover, they have a narrow bandwidth and high-cost fabrication techniques. Our project aims to design a reliable textile patch antenna design system for wireless communication, and produce it using the low-cost material and low-cost technique of thermal transfer printing by using the clothes iron. These images show the proposed textile antenna. The antenna is fabricated using a new technique called thermal transfer printing by using the clothes iron. It is printed using a low-cost conductive carbon. When we test on the design durability, the textile patch antenna is able to withstand the flexibility test and stretching test without affecting the RF performance, and is also able to sustain the performance under the washing test. In this section, we will be showing you on the detailed process of thermal transfer printing. The following is the textile antenna design dimensions. Next, we will have a look on the antenna development process flow. The process begins with the modification of the ink cartilage. Instead of using conventional ink, conductive ink is used. The conductive ink is transferred to the cartilage. As you can see here in figure C, we have used a normal office printer for this project. Next, the printing is done on a heat transfer paper. This is followed by a manual thermal transfer. Using a cloth iron, this thermal transfer method is applied by melting a coating of ribbon so that it stays glued to the fabric substrate. Finally, the textile antenna, as well as the final design of textile antenna, is shown in figure F and figure G, respectively. The antenna was first tested using AV transmitter to transmit an AV signal to the AV receiver. The AV receiver, which has been fixed to a television to display the receive AV signal from the transmitter. This is the prototype of the textile antenna as the transmitter. When tested, the antenna is able to transmit 3 meters away without any signal loss from the AV receiver. In the test TS5828, a 5.8G model transmitter used to transmit the signal. For the second test, the fabricated antenna was fixed with an RC832 receiver to receive the AV signal. This is the prototype of the textile antenna as the receiver. The antenna connected to the receiver, and the transmitter brought further away. In the test, the distance able receives by the fabricated antenna 3 meter. Now, let's discuss the benefits of this project. Firstly, the low-cost antenna is affordable to develop by any users. Next, it can be printed using low-cost material, the conductive carbon. This technology can be applied in green application, where the technique doesn't use the conventional process, using the etching process, and eventually reduce the chemical waste. And finally, our project has high conformability, robustness, ease of integration, and is concurrently comfortable without degrading the RF performance. So, what are the commercialization potential? Where this technology can be applied, it can be applied in firefighters saving garment and life jacket. Recent field trials with the antenna show that someone lost at sea wearing a life vest equipped with this new technology. Indoor system monitoring for elderly people in nursing home. In order to protect the elderly, they are equipped with the sensor and wearable antenna on the cloth, with which an alarm can be triggered in danger or emergency situation.